we're going to do today is the last part of Chapter 7. And the last part of Chapter 7 basically is just reviewing problems. So we're going to solve a whole bunch of molarity style problems. And then we're going to look at the serial dilution, do a couple dilution experiments or demonstrations, problems, and look at a tutorial. Remember, at the end of class, we will have a little quiz. It's very simple. It's based on tutorials, first two tutorials from the chapter. And I will use this as midterm verification to prove that you really are here, okay? I have to have something in writing to prove you're here. So this will work. Yeah?
Does the quiz count toward their grade?
Of course it does.
Ah.
It'll count just like extra credits do and stuff like that. Okay? All right.
But we didn't know that we're gonna have that quiz.
I'm sorry?
I didn't know that we're gonna have that quiz.
I sent everyone an email.
So yeah, I was sleeping.
Oh.
And then I have class 8, so I didn't check my email.
Oh. I'm sorry?
I didn't get one.
Didn't get an email?
No.
Well, I did send it. Actually, one bounced back. You might check your email on Blackboard, make sure it's in properly. All right, we were talking about molarity, solutions and molarity. Very simple concept, really. To calculate molarity, that's an uppercase M. You simply take moles of solute and divide it by the volume of your solution in liters. Now, there are 3 tutorials for Chapter 7. Let's go ahead and look at the first. This is very simple. I gave everyone a printout of the problems we're going to be working today so that everyone can play along. Doing these types of problems is very important for this next exam. All right, here we are given a molarity, we are given a number of moles, and we simply have to calculate a volume. Doesn't really matter how you remember the process here, but you need to remember one equation, okay? It could be concentration times volume is moles, or it could simply be concentration, that is molarity, is moles divided by volume. Just remember one of them, and then all you do is just simply solve. Here, in order to get volume, what you want to do is take the number of moles and divide it by the concentration. So why don't you quickly do that?
425.
Here's our number, 0.655 divided by 0.154, 4.26 liters. Now we are given molarity, and we are given a volume. All we have to do here is calculate the number of moles. Now this is one of my favorites. Concentration times volume is moles. We'll see why that's so important when we do dilutions, because we'll use that constantly when we do dilutions. Concentration times volume is moles. So we have 0.125 times our volume, 2.92 liters. 0.365 should be the answer. Now the second tutorial, to do with simple calculations, basically takes the same types of problems, except puts them into Word format, and then requires you typically to do some sort of a metric conversion. Here we're going to convert from liters to milliliters. We are given a concentration, 0.0555. Methanol is what we have, and we're looking for 0.037 moles of methanol. So we're looking for a volume. Now we're going to solve it first in terms of liters, and then we're just going to multiply by 1,000 to get milliliters. Moles divided by molarity. This is going to give us our volume. Do our simple calculation. We get 0.666 liters times 1,000, 666 milliliters. Now the next set of problems are old exam questions. Everyone loves these. We have a solution as 10 grams of sodium hydroxide in 500 mils of solution. What we have to do is simply pick the proper concentration. Now remember, molarity is simply going to be the number of moles of sodium hydroxide, in this case, divided by our volume in liters. That's a common mistake, people not converting it to liters. Don't do that. Moles of sodium hydroxide. Well, here we have a mass, and we have a molar mass. The other thing I like to say is mass over molar mass is moles. So this gives us moles divided by liters. 10 divided by 40 divided by 0.5. Grams cancel. We have 0.5 molar. Let's work the next one. We have calcium nitrate. We're looking for a mass. How many grams do we have to dissolve to make 500 mils of a 1 molar solution? Now you can tell this is a real exam question because, you know, the numbers are nice and exact and easy and stuff like that. We're looking to make half a liter. We want it to be 1 molar. Well, let's just think about this. If we wanted to make a liter of 1 molar solution, we would simply take 164 grams, wouldn't we? So we're going to make half a liter. We're going to need half of that. So that's a good place to start logically. Moles is going to be our concentration, moles per liter, times our volume. 0.5 times 1, liters cancel. We're looking for half a mole of calcium nitrate. Now, 1 mole of calcium nitrate weighs 164. We can use this as our new given. Our molar mass, here is our ratio. Moles will cancel. And we have 82 grams to 2 significant figures. The next one, you had to show your work. So it's very simple. We have a concentration of 0.375 moles per liter. We have 4.75 liters of it. How many moles? Concentration times volume gives us moles. This is in liters, that's good. Again, just multiply concentration times volume. Here's our concentration, there's our volume. We're looking at 1.78 moles. Another multiple choice. 200 mils of sodium chloride solution evaporated down gave us 1.56 grams of sodium chloride. What was our molarity? Well, as always, our molarity is simply going to be the moles of sodium chloride divided by our volume here, which is 0.2 liters. For moles of sodium chloride, well, we evaporated this stuff down and we got about 1.5 grams. Molar mass is 58 grams per mole. So this equals moles of sodium chloride. Once again, do our simple math. And we have 0.133 molar. Bleach. I've said it several times. Bleach is what is this stuff called? OCl. What's the polyatomic ion? Chlorate is ClO3. Chlorite is ClO2. And ClO is hypochlorite. So, this is sodium hypochlorite. Standard bleach, again, is about 0.7 molar. This is our molar mass. How many grams of sodium hypochlorite are there in a liter of bleach? Well, we're looking for a mass. What we actually have to do is figure out moles first, don't we? Because once we know the moles of sodium hypochlorite, and we know its molar mass, we can calculate mass. Again, this is just going to be concentration times volume, 0.7 moles per liter. Our volume here is 1 liter. We're looking at 0.7 moles. Now 1 mole weighs 74 grams. All we want to do is take our given here, 0.7, multiply it by our molar mass. Moles will cancel. And we get about 52.1 grams. In a gallon of bleach, if you are at the point in your life where you buy things like bleach, you know, it's a couple dollars or something like that, you'd get about, what, 200 grams of hypochlorite in your bottle. That amount of sodium hypochlorite actually costs about 3 cents. The bottle costs more than that. You know what the real price of it is? It's the liability insurance, in case somebody decides to drink it. and then soup. What volume in liters of a 1.71 molar solution of KCl would you need if you wanted 21.1 grams of KCl? Well, 21 grams of KCl is a certain number of moles, isn't it? So we need to figure out how many moles we're dealing with. Once we know how many moles we have concentration, and we'll know moles. We can therefore simply solve for volume. We need to convert our mass to moles. Once we have moles and our concentration, we simply solve for our volume. The stuff weighs 74.55 grams per mole. We have 21 grams. This is mass divided by molar mass, isn't it? And that gives us moles. So we have 0.283 moles of KCl. We have 1.71 molar. In order to get the volume, we simply need to take our number of moles divided by our concentration. Again, moles will cancel here. And we get 0.165 liters. We're going to make 1 liter of 0.1 molar sodium iodide. Once again, obvious test question, everything says ones, right? Obvious test question. How many grams of sodium iodide? Well, if we were going to make 1 liter of 1 molar, just off the top of your head, we need 149 grams, right? So, if we simply take our concentration, which is 0.1 moles per liter, and our volume, 1 liter, liters will cancel, and we're looking for 0.1 moles. We know the molar mass, and we know the number of moles we need. Simply multiply the number of moles by our molar mass. Moles will cancel, and we need to 3 significant figures, 15 grams of stuff. Any questions on these? All right, this next question on the sheet is actually a fairly interesting limiting reactant problem. Okay? Where you get to do simple calculations. We are reacting barium nitrate and sodium sulfate. We know that these are going to react and form barium sulfate, which is very insoluble. It will come falling out of solution as this fluffy white solid. We'll also be left with sodium nitrate in solution. Now, we want to know how many grams of barium sulfate we're going to get if we take 15 mils of just about 1 molar sodium sulfate and react it with excess barium nitrate. So this isn't what I was thinking about. This isn't the limiting reactant one yet, but we'll get there. So here we have excess barium nitrate. So we have all of this we need. What what we're doing is simply taking just about 1 molar stuff here, 15 mils of it, and we're going to make solid barium sulfate. What we need to do is to realize that every mole of sodium sulfate is going to give us 1 mole of barium sulfate, right? So we know a concentration and a volume. So we know how many moles of sodium sulfate we have, right? Once we know how many moles, we know how many moles of this we should get. And once we know how many moles, we can figure out how many grams we should get. All right, here it is in writing. In order to calculate grams, we need to know how many moles of our sodium sulfate we have. Again, 15 mils, just about 1 molar. Once we know the number of moles, simply multiply it by our molar mass. Okay. Moles of sodium sulfate. This is going to be, not surprisingly, concentration times volume. Concentration times volume is moles. Our per liter cancel, and we have 0.01497 moles of sodium sulfate. Remember to change milliliters into liters by dividing by 1,000. All right, so now we know how many moles of sodium sulfate. That's the same number of moles of barium sulfate that we should form. If we simply take the molar mass of barium sulfate and the number of moles we should get, moles here will cancel, and we'll be left with grams of barium sulfate. 0.015 times 233, with 3 significant figures, 3.49 grams of product. Now, if we did this in lab, and you actually collected the barium sulfate, and you weighed it, you could then calculate a yield, couldn't you? That would be the actual yield over the theoretical times 100. Speaking of that, look at this problem. Pretend we just did this in lab. And tell me what the yield of this particular reaction is. We're taking potassium chloride, reacting it with silver nitrate to get silver chloride. We have 1 mole of each reactant, and we get 125 grams of product. Once again, this is very obviously an exam question, isn't it? Because we have exactly 1 mole. Nice, easy numbers. If we took 1 mole of KCl and reacted it with 1 mole of silver nitrate, how many moles of silver chloride should we get? 1. Right? How much does 1 mole of silver chloride weigh? You need to calculate that, don't you? 143. All right, take those numbers. I'll pause for a moment. Calculate a percentage yield for me. If we expect 1 mole of product, that 1 mole of product should weigh 143.32 grams. In fact, we get 125 grams. So our percent yield is simply the actual yield divided by our theoretical yield multiplied by 100. Or 87.2%. Any questions? All right, let's look at this guy. This really is a limiting reaction problem, isn't it? This is what I was thinking of. We have 1 liter of half molar barium chloride and 1 liter of 0.2 molar potassium chromate. We get solid barium chromate coming out. What will be the concentration of barium in solution at the end of the reaction? All right, so what we're doing here, if you think about it, we have 1 liter of each, don't we? But barium is higher concentration. So that means we have more barium than we do chromate. So we will precipitate out barium chromate, but because we had excess barium, there'll be some barium left over in solution. Right? Makes sense. Our stoichiometry here is all 1-to-1. Let's look and see how many moles of barium chloride we have, how many moles of potassium chromate we have. That will tell us how many moles of this stuff we're going to get. Once we know how many moles we're going to get, that will tell us how much barium is left over. Trivial, isn't it? All right, for barium chloride, we have 1 liter at 0.5 moles per liter, or half a mole. For potassium chromate, we have 1 liter at 0.2 moles per liter, or 0.2 moles. Now, 0.2 moles of barium is going to react with our chromate, isn't it? So we're going to be left with 0.3 moles of barium left over. Now, the one trick that you have to pay attention to in this type of problem is to remember that we've mixed 2 solutions together here, haven't we? We took 1 liter of each. Our total volume now is 2 liters, right? So if we want to calculate the concentration, we have 0.3 moles in 2 liters. 0.3 moles in 2 liters, 0.15 moles per liter. When you're adding solutions together, always remember to sum up the volumes. Any questions? All right, this was on one exam. This one was on another. We have 3.2 liters of 0.75 molar lead nitrate. We are going to mix this with 7.4 liters of 2.3 molar lead nitrate. What is our final concentration of lead nitrate? No, don't need Avogadro.
No, I said 0.7.
Oh, okay. What you have to do, again, we're taking 2 solutions and mixing them. So we need to remember that our volume, our new volume, is going to be the sum of the 2 volumes, right? That makes sense. For each solution, we have a concentration and a volume. So that's a certain number of moles, isn't it? So we're going to add the number of moles. We're going to add our volumes. And that will give us our final concentration. For each of these, calculate moles of lead nitrate. Add them together. That gives you your total number of moles. Then you want to add the 2 volumes together, 3,2 and 7,4. Divide it all together and get the concentration. I'll pause for a minute while you calculate moles for each of these. .2 liters, 0.75 moles per liter. We have 2.4 moles of lead nitrate in our first solution. Our second one, 7.4 liters, 2.3 moles per liter. We have 17 moles. Our total number of moles is therefore going to be 17 plus 2.4. 19.4. Our total volume is simply 3.2 plus 7.4, 10.6. Divide them together, and we have 1.8 molar. Any questions on these? Same types of calculations over and over and over again. Once you master it, it's simple. All right, here's a different way to ask this. I have a solution with 9.36 times 10 to the 27 molecules of nitric acid. I'm going to take these and put them in 1,000 liters. What is my concentration? Well, if we had 1 mole of nitric acid, we would have 6.02 times 10 to the 23rd molecules, wouldn't we? So to convert our molecules into moles, all we have to do is divide by Avogadro's number. Once we have moles, we simply divide by our volume, and we get concentration. Number of moles of nitric acid, that's going to be from Avogadro. So our given number of molecules divided by Avogadro's number, then we want to take that and divide it by 1,000 liters of solution. We are given that we have 9.36 times 10 to the 27 nitric acids. 1 mole is 6.02 times 10 to the 23rd. Simply do our division, and we have 1.56 times 10 to the 4th moles. Now to get our concentration, we simply need to take our number of moles divided by our number of liters. So we're dividing by 1,000, aren't we? And this gives us 15.6 moles per liter. This is what is referred to as fuming nitric acid. Fuming nitric acid, concentrated nitric acid, it's called fuming because if you look at the air above it, you're getting nitrogen oxide fumes, brown, in 204. In equilibrium with the nitric acid dissolved in the water. This is very, very strong stuff. If you touch it to your skin, it will instantly burn it. You'll be left with an ugly brown mark. Wash it off quickly, please. But you'll be left with an ugly brown mark. You certainly don't want to breathe it and whatever. Turns out, have you ever heard of a Scud missile? I'm sure you have. They have them, North Korea makes them, sells them to everybody. A Scud missile uses concentrated nitric acid as the oxidant for its fuel source. So in this big long missile, you've got a tank filled with fuming nitric acid. Now, during the first Gulf War, I believe, there were Scud missiles being fired, at everybody and stuff, which is a bad thing. But we had the Patriot anti-missile missile, remember? And it could zoop up and shoot these things down in midair. And that was a good thing, because it didn't blow up when they hit the ground and stuff like that. But the bad thing is that all of this, these gallons and gallons, 1,000 liters or so, of nitric acid that were in these were suddenly released in this giant aerosol cloud. And if you happen to be one of the guys firing the Patriot missiles, that was a very bad thing, because it was kind of like raining fuming nitric acid on you. So, bad thing to shoot it down. Any questions? All right, let's go ahead and move to our last topic, and this is dilutions. Dilutions, what we're doing in a dilution problem is we're taking a solution of known concentration and we're adding water to it. We wind up with a bigger volume, and all we want to do is calculate the concentration. Simple. The thing that makes it so simple is that we have our original solution. If we know how much of this and we know its concentration, we know how many moles we have, right? Now we go and we add water. The moles don't change, but the volume does, that's all. We can express this mathematically, knowing that concentration times volume is moles. We can say our initial volume times our initial concentration will give us how many moles we start with. Now we go and we add water to it. We get a new volume, we'll call that V2. And we get a new concentration. But the number of moles is the same. So we can equate these two. V1, C1, V2, C2. Concentration times volume is moles. So they're really very simple problems. Here we have sodium chloride at 0.53 molar. We take 500 mils. When you take part of a solution, it's called an aliquot. So we take a 500 mil aliquot and dilute it to 1750 mils. What is our final concentration? I see the problems sound complicated, but they're not. Because we know a concentration and a volume. The number of moles doesn't change. We do our calculation to get our number of moles, volume times molarity. We're going to set up our equation relating the initial and the final state and simply solve for our final concentration. V1, C1, V2, C2. We plug in here our volume, 500 mils, or 0.5 liters. Our concentration, 0.53. Our final volume, 1.75 liters, and we don't know our concentration. Write it out like this. All in the world you have to do is take 0.5 times 0.53 divided by 1.75, just like this. We're at 0.15 molar. Any questions? Concentration times volume is moles. The moles do not change. We have a 2.1 molar solution. That's our stock solution. You know, like when we do lab, we have the bottles. They all have a concentration on them of some sort. Well, we actually don't need 2.1 molar. We need 1.1 molar. So what we're going to do is take our 2.1 and we're going to dilute it So we wind up with 1,600 mils of 1.1 molar. Number of moles isn't going to change here, is it? We're looking for 1.6 liters of 1.1 molar. That's a number of moles. We know our initial concentration, that's 2.1, and we're just looking for the volume here. So we write our magic equation. C1V1, C2V2. We know our initial concentration is 2.1. Our final is 1.1. And our final volume is 1.6 liters. So we plug all these things in, solve for V1. 1.1 times 1.6 divided by 2.1. $840 milliliters. So what you would do in lab is you would take 840 mils of your stock solution and you would dilute it to a final volume of 1,600 mils. Any question? All right, when we started all of this, I had this little dilution scheme up on the opening slide. What you're doing in this dilution scheme is you're taking a stock solution. We're taking 10 mils out of it and adding 990 mils of water. Mix it up, and we get our first solution. Now I'm going to take 10 mils of this one, add it to 990 mils, mix it up, and get my second. Do it again, get my third, one more time to get my fourth. What I want to know is what's the final concentration down here in number 4. Now you see what you want to do here. We have a concentration and a volume for our first thing here, don't we? Our 10 mils we pulled out, and we know its concentration. So we know how many moles we're putting in here, right? If we know how many moles and we know its volume, volume's going to be 1 liter, then we know a concentration. Now again, we pull out 10 mils to 1 liter. Calculate its concentration. Do it again, and do it again. Let's see how this works. We're going to calculate moles using volume times molarity for each of these steps. We're at 1 liter for each, so the number of moles directly gives us moles per liter. For our first step, 0.53 moles per liter. We have 10 mils, that's 0.01 liters. We have 5.3 times 10 to the minus 3 moles. For our second step, Since it's 1 liter, this is 5.3 times 10 to the minus 3 molar. Okay? For our second step, we have 10 mils and 5.3 times 10 to the minus 3 moles per liter. They cancel. And we have 5.3 times 10 to the minus 5th moles in 1 liter. That's our concentration for our third step now. Again, 10 mils, 5.3 times 10 to the minus 5th. We're at 10 to the minus 7 moles.
The reason you do with the scientific notation because the numbers will be impossible. That's why, like you do like 5.3 times
Yeah.
because it will be like not impossible, but
It'd be very difficult to do the dilution
right.
correctly. Finally, we're at 10 to the minus 7 molar. We do our last one. 0.01, 5 times 10 to the minus 7. We are at 10 to the minus 9 moles per liter. So that's our final concentration. Now, you know when you're doing serial dilutions like this, it's actually fun to think about what you've got in the pot when you're done. How many sodium ions are in this final pot? Oh, that's actually simple, isn't it? Because we know how many moles. And we know how many sodium ions there would be in 1 mole. That's Avogadro's number, right? So to calculate the number of ions, we simply take our number of moles, our ions per mole, moles cancel, and we can calculate that we have about 10 to the 15th sodium ions. Now, you know, that's still a big number, 10 to the 15th. But what if we would have continued to do this dilution over and over again, say up to, say, 7 or 8 times? What do you think? If we did 7 more dilutions, did this calculation, there would be 32 sodium ions in our liter. 32, believe it or not. Ever heard of homeopathic medicines? Do you know how they make homeopathic medicine? You start off with something like this, and then you do, like 12 or 13 serial dilutions. And so when you're done, you've got, I don't know, 15 or 20 ions per liter. So you could look at that and say, gee, there's nothing in there. And you'd be right. So next time you see a homeopathic medicine with a big fancy price tag and a fancy name, homeopathic, sounds neat, right? Remember, there's nothing in there. All right, there's a dilution tutorial. Let's run through these quickly. I think there are 3 or 4 on your sheet. To what final volume should we take 140 mils of 2.3 molar stuff to get a final concentration of 0.56 molar? We're going to use Concentration times volume. Here we have a concentration, here we have a volume, so we know the number of moles. Here we have our final concentration, we just need our final volume. Our final volume is going to be concentration 1, volume 1, divided by our
575.
concentration number 2, 0.58 liters. And finally, the problem asks for this in milliliters, 580 mils. Standard formula. 440 mils, 0.05 molar. Our final volume here is 0.88 liters. What is our final concentration? B1, C1, B2, C2. All we're doing is solving for C2. Final concentration is going to be initial concentration, initial volume, divided by our final volume. We are at 0.026 molar. One more. How many liters of solvent do we have to add to 640 mils of 2.8 molar to give a final concentration of 0.9? Now I'll hush here for a second. Let you think about this one.
So we are solving for volume.
We have a concentration and a volume. We have a concentration. We will know our total volume, won't we? We calculate our total volume. But this problem is slightly different because we're starting with 640. That means we're going to have to add so many milliliters to it in order to make this final volume. So, our final volume, we can calculate, is going to be 2 liters. But we started with 0.64 liters, didn't we? So how much do we have to add? 1.4 liters. Any questions? All right, let's end this up with what's going to be an introduction to Chapter 8. Remember in lab, way back when we did lab, one of the things that you did was to take acid solutions and added base to them, right? And phenolphthalein and stuff like that. You got to change. What you're doing here is called a neutralization. Sulfuric acid is a strong acid. Sodium hydroxide is a strong base. When you combine them together, you get a salt, in this case sodium sulfate, and water. That's something worth remembering. An acid plus a base gives a salt and water. We start off with strong acid, strong base, and we wind up with a neutral solution. All right, what we've done here, we took 300 mils of our sodium hydroxide. We saw that that reacted completely with 100 mils of a sulfuric acid solution. What is the concentration of our sulfuric acid solution? Look at our equation. 2 moles of hydroxide react with 1 mole of sulfuric acid, right?
And we make 1 mole.
If we did concentration times volume, we would know how many moles of sodium hydroxide we had, right? If that reacted completely with the sulfuric acid, then that means if we know how many moles we have here, we must have well, we can calculate the number of moles of sulfuric acid. Okay. 2 moles of sodium hydroxide for every mole of sulfuric acid. Calculate the number of moles using concentration and volume. That gives us the number of moles of hydroxide, right? Takes 2 hydroxides for every sulfuric acid. So we multiply that by 2 to get moles of sulfuric acid. Once we know moles, divided by our volume, and we get concentration. This is what is referred to as a titration. We are taking a strong acid and a strong base, we're mixing them carefully until we get a neutral solution. Moles of sodium hydroxide, concentration times volume. We have 6.45 times 10 to the minus 3 moles. It takes 2 hydroxides for every sulfuric acid. How many sulfuric acids do we have? 2 hydroxides for every sulfuric acid. Sodium hydroxides cancel. We simply take this, that's what I thought. I thought I made a mistake on that slide, and divide by 2, not multiply. We have 3.23 times 10 to the minus 3 moles of sulfuric acid. Finally, if we know how many moles and we know our volume, it's 100 mils. Moles of sulfuric acid divided by the volume of sulfuric acid in liters gives us a concentration of sulfuric acid. Any questions? All right, thus endeth